Okay, so it's time, so let's get started. So we are very happy to have Professor Bumin Yenmez from Washington University. Please, me, one or two, and to meet. So to introduce him, Bumin is originally from Turkey and came to the United States for college primarily, and he got a bachelor's degree of computer tech, where he began to study and research in economics. And then he went on to Stanford GSP and got PhD in 2010. Then he went on to be a postdoc at Microsoft Research. He was a faculty member first in Carnegie Mellon and then Boston College until the last year. Yeah, 2003, I think. Okay, good. And then now moved to Washington State. So he has a lot of important research in economics and matching theory in particular. And I was believe me, I prepared a lot of things to say about his research, but I think instead of me saying anything about it, I think he's going to present today and then tomorrow and on Friday. So you are all welcome to attend. Okay. And I'm really comfortable sharing you with me. So on that note, please.
This is the first lecture of the mini lectures. There will be 3 of them. So in the first lecture, we're going to talk about two-sided matching markets. We're going to introduce a solution concept called stability, and we will study the basic theory of stable matchings. In the second lecture, we're going to study mathematical objects called Matroids. So Matroids have been used in discrete mathematics, combinatorial optimization, and other areas. And we're going to apply them to a matching context. And finally, in the last lecture, we're going to look at the deferred acceptance algorithm more closely, and we're going to study different properties of the deferred acceptance algorithm. That has been the algorithm to study both in theory and also it's been implemented in practice. So what are two-sided matching markers? Let's start with a few examples. Most labor markers that we consider are actually two-sided matching markers. For example, you can think about workers on one side of the market and firms on the other side of the market. So workers need to be matched with a firm, and firms need to match with workers. There are many other examples that have been studied in market design literature, such as matching doctors with hospitals. In the context of Japan, this was actually more complicated than the standard models that we've analyzed, because in Japan there are regions, and the government wants to limit the number of doctors in each region to get a more equitable distribution of doctors. And there are others. There are also education markers that we study in practice. For example, we want to match students with public schools or students with universities. So this is also a prominent example of a two-sided matching market, because usually we view public schools as non-strategic agents. So they are not strategic. So therefore, this is slightly different than, say, the worker-firm matching problem, in which all agents may be strategic. And finally, we can also match students with different courses. Other examples are also important. For example, we can assign employees to different tasks in a company, or we can assign employees to shifts. For example, nurses need to be assigned to different shifts, day shifts, evening shifts, weekend shifts, holiday shift, and this becomes an important two-sided matching problem. For today's talk, our main references are going to be Gale and Shapley. So this was the original paper that started the study of market design. It was published in 1962. The other two papers are Roth 1984 and Hetfield and Pickera. Both these papers generalized Galen-Shapley's model to accommodate more markets. So if there are no questions about the motivation or the markets, we can now look at the model. So we're going to look at a two-sided matching market. On one side of the market, we're going to have the set of schools, right? The set of schools is denoted by calligraphic C. On the other side of the market, we have students, and the set of students is going to be denoted by calligraphic S. Okay, students and schools. We're interested in assigning students to schools. However, there can be more than one way in which a student can be assigned to a school. For example, the student can get a scholarship, or there could be different programs within the school that the student can be assigned to. Therefore, we're going to use contracts. A contract is going to be denoted by, say, the letter X. It's going to specify a student, a school, and the terms. And the terms could include financial aid. So therefore, this matching market could be either a transferable utility setting in which agents do exchange money, or it could be a non-transferable utility setting in which agents actually do not exchange any money. And the set of all contracts denoted by calligraphic X. Sometimes we're going to be interested in the set of contracts that belongs to a particular agent. For example, take a student S, and given any set of contracts X, the set of contracts associated with student S is going to be denoted by XS. Right? So these contracts name student S. These are the contracts that the student can have. Likewise, we're going to be interested in contracts associated with a school C in a set X, and those are going to be denoted by set XC. So we have our agents. Now let's talk about preferences of the agents. Each student is going to be endowed with a preference relation over all the contracts that she can have and the outside option. Okay? So this is going to be denoted by succeed or Z equal to for student S. The student can rank all the contracts that names her and an outside option. The outside option is denoted by the empty set. This could be going to a private school. So this could be moving to a different city, or this could be being homeschooled. The strict part of this preference relationship is denoted by succeeds. And we're going to say that a contract X is acceptable to students if the contract is more preferred than the outside option. Right? If I'd rather take my outside option, that means the contract is not acceptable. Otherwise, it is going to be accepted. So these are the preferences of students. What about the schools? Now, the schools are going to have more complicated preferences because a school can be assigned to more than one student. We're going to model schools' preferences as a choice rule. School C's choice rule is going to be denoted by CH of C. And given a set of contracts, this choice rule produces the subset that's going to be chosen by the school, right? The school gets a set of contracts, a set of applications. The school needs to decide which contracts to accept and which contracts to reject. So all that admissions information, admissions rules is summarized by the choice rule of the school. And finally, what's our solution concept? Given the preferences of the agents, we would like to find a desirable outcome. A desirable outcome first needs to be a matching. Okay? A matching is going to be a set of contracts X, such that for each student, they cannot give the student more than one contract. Each student can be assigned to at most one school. Each student can have at most one contract. So that's an outcome in our setting. So what is a good outcome? we don't only want an outcome, we want a good outcome. So what are the desirable properties of a good outcome? So we're going to use this solution concept that goes back to Gale and Shapley called stability. Stability has two properties. The first one is individual rationality. Okay? So a matching X is going to be stable if it is individually rational and if there are no blocking pairs. Now, what does individual rationality mean? Individual rationality means for each student, the assignment of the student is weakly more preferred than the outside option. So it is okay for the student to be unassigned or to get the outside option, but the student cannot be assigned to an unacceptable contract. And for each school C, the choice from the school's outcome must give the school's outcome back. If these are the contracts assigned to the school and the school applies its choice rule, the school needs to choose all the contracts, right? So these are the students assigned to me. I apply my choice rule. I'm going to accept all of them. I'm not going to reject any of them. So that's individual rationality for a school. And finally, there shouldn't be any blocking pairs. So what does that mean? For each school S and for each student S and for each school C, if X is a contract that they can sign, if the student prefers contract X to her outcome in this set XOS, then the school shouldn't choose the contract X if the school considers X together with the set of contracts that it gets in matching X. So I'm the school, and a student wants to be assigned to me with a particular contract X. Now I consider all the contracts that I already have with that new contract. I shouldn't be choosing that contract X. If I choose the contract X, then the student S and the school C form a blocking pair. And we don't want such blocking pairs for stability. Okay. Now, you can define stability by generalizing this notion of blocking. So here we're just considering one particular contract. And then we say that the student and the school form a blocking pair via this contract X. You could provide a similar definition using sets. But it turns out that under our conditions, set by stability and pair by stability are equivalent. So therefore, it is sufficient for us to consider blocking pairs with only one contract. Now, we've defined the set of agents participating in the market. We've defined their preferences, and we've defined a good solution concept. So the question now we want to impose is whether stable matchings exist. Do stable matchings exist? The answer turns out to be no. So in some markets, stable matchings do not exist. Let's consider the following example. There is only one school C. There are 3 students, student 1, student 2, and student 3. Each student and school can have one contract only. X1 is the contract between the student, the first student and the school. X2 is the contract of the second student with the school. And X3 is the contract of the third student with the school. Okay? So each student-school pair defines a unique contract. So what about the preferences? Well, each student likes their contract more than the outside option. So all contracts are acceptable for the corresponding students. What about the choice rule of the school? Well, the choice rule of the school works as follows. If all students apply, the school chooses the empty set. If only students 1 and 2 apply, the school chooses the first student. If the first and the third students apply, the school chooses the third student. If the second and the third students apply, the school chooses the second student. If only one student applies, the school chooses that student. Okay, so this is the choice rule of the school. So I'm going to keep the choice rule of the school on the next slide. And I'm going to argue that in this market, there is no stable matching. Why is that? Well, remember individual rationality for the school. It says that if X is a stable matching, right, then when we apply the choice rule of the school to the contracts assigned to the school, we must get it back. The school must be happy with the set of contracts assigned to it. Now, we have, look at the choice rule of the school. The choice either chooses nothing or one contract. So the school always chooses either the empty set or one contract. That means this set XC can have at most one contract. Right, so we have 4 options. So XC can be the empty set, the first contract, the second contract, or the last contract. Now I'm going to argue that each one of these 4 sets is actually blocked by a pair. So if you look at the empty set, now, if the matching is the empty set, now the first student wants to be assigned to the school, right? Because X1 is acceptable to the first student. And if X1 is the only contract, then the school is going to choose that contract. Therefore, there is a blocking pair, including the first student and the school, and the contract they use is X1. So this cannot be a stable match. If the matching is the set including only X1, now the third student wants to be matched with the school because X3 is an acceptable contract. And now if the school considers X3 together with X1, the school chooses X3. That means the third student and the school form a blocking pair using this contract X3. You can repeat the same exercise for the third matching and the last matching. And in each case, there's going to be a blocking pair. So our conclusion is that the existence of a stable matching is not guaranteed. So in some markets, stable matchings do not exist. So what do we do? So we give up and we go back home. Stability is not a good solution concept because we can't always find stable matchings. So we can investigate if there are conditions, there are assumptions under which stable matchings exist, right? So there are 2 pathways in research. Now, one of them is you look at another concept other than stability, and you study the existence of matchings satisfying this second property. Or you can look at conditions under which a stable matching exists. Because stability, we believe that the stability is the right notion, the concept, then we investigate whether there are assumptions under which stable matchings are guaranteed to exist. Okay? So when do stable matchings exist? So if you look at this example, for students, everything is so simple. There is one contract, and the student finds the contract acceptable. So what is kind of non-standard is perhaps the choice rule of the school, right? If every student applies, the school chooses the empty set. So otherwise, looks like there are some cycles going on here. So there is something going on with the preferences of the school. So we would like to investigate if we can make assumptions on the choice rule of the school such that a stable matching is guaranteed to exist.
Sorry, I wonder. Let me ask very in you defined question. So you kind of said that something is wrong about the choice rule. I mean, it seems here. One is that from X1, 2, and 3, empty set is chosen. Between these sets with 2 contracts, there seems to be something like a typo. And so I wonder whether there's any sense in which which of these 2 things are culprits of this example. I do not have a very good.
Yes, so we identified two things that look kind of weird, right? The first one is that the school is choosing the empty set when everybody is applying, and the second thing is like there seems to be some cycles here. It turns out that even if the choice from the set of all contracts is either only X1 or only X2 or only X3, still there's not going to be any stable matching. So we could avoid the first situation. However, because of the choices here, still there won't be any stable matchings. So now, so what is the condition violated? So let's try to figure that out. So we're going to use this notion of path independence defined by Charlie Platt in 1973. So Charlie Platt used this condition to study social choice. However, it's been used in matching theory afterwards as well. So what is path independence? So a choice rule is going to satisfy path independence if for every set of contracts, X and X prime, the choice from the union is equal to the choice from the first set, union, second set. So this will imply the following. Given any set of contracts, we can chop it up into smaller pieces. These smaller pieces can have overlap, or maybe they don't. And then we can apply the choice rule to any of the smaller pieces. And at the end, we can apply the choice rule again to the all chosen contracts. And the final outcome will always be the same. So it doesn't matter how you chop up the set into smaller sets. You will always get the same outcome. For example, think about graduate student admissions. So how do we normally do it? Well, there's a faculty in charge of the admissions. But this faculty assigns a set of applications to different faculty. Each faculty gets a set. Each faculty applies the criteria for admissions and shortlists some students, and then sends it back to the faculty in charge. And finally, the faculty in charge applies the admissions criteria and chooses the set of students who are going to be admitted. As long as each faculty applies the same criteria, and as long as these criteria give us a path-independent choice rule, it doesn't really matter who gets which set, how these batches are formed. At the end of the day, we're always going to admit the same set of students, right? So path independence is a desirable property in many contexts. So you may have heard about substitutability. So substitutability is actually slightly weaker than path independence. In other words, substitutability is implied by path independence, but substitutability does not imply path independence. So it turns out that path independence is equivalent to substitutability plus another condition that is called either consistency or irrelevance of rejected contracts. Yes, please.
So path independence says that after choosing from X prime, and then I union X prime to X, and then I choose from this set. But how about if I first choose from X prime, then I choose from X, and then I union the two sets that I chose.
So this is a very intuitive like definition of path independence. It turns out that these two definitions of path independence are actually equivalent. So it's easy to see that this property will imply that property, but you can also show that that property implies this property too.
Okay.
Thank you. Right. So we're going to impose path independence. Let's look at our example where there was no stable matching. So I'm going to argue that in this example, path independence is violated. It is not satisfied. So why is that? Well, let's look at the choice from set of all contracts. So this is empty set. Or in our modified version, this could be X1. Now I'm going to chop this set into smaller sets. So the first one is going to be x1, x2, and then I'm going to apply the choice rule, and then I'm going to take the union with x3. Right? The choice from x1, x2 is equal to x1. Now I take the union with x3, I get this set. And the choice from the set that has x1 and x3 is equal to x3. And these are different. So therefore, path independence is violated. So note that depending on how you chop this up, this could be equal to x3 or x1 or x2. So regardless of how you define the choice from the set of all contracts, path independence is always going to be violated. So one thing to note here is that this substitutes condition is indeed satisfied. So the substitutes condition can be defined as follows. If a contract is chosen from a set, and we remove some other contracts and look at the remaining set, the same contract should be chosen. Or in other words, if you look at the set of contracts that are rejected, this rule, the rejection rule, should be monotone. So note that, okay, so let's look at the set of contracts that are rejected. From here, we are rejecting x1, x2, x3. From here, we are rejecting x2, x1, x3, empty set, empty set. So this choice rule indeed satisfies the substitutes condition, and yet there is no stable matching. So substitutes alone does not guarantee the existence of a stable matching. We need path independence. Now, we've seen a choice rule that is not path independent. Now, let's look at choice rules that are path independent. So let's consider the following case first. School has a capacity denoted by QC, and the school can rank all contracts according to a preference relation. Right? I can rank all the students or all the contracts linearly, and I also have a capacity. Then what is my choice rule? So this is the so-called responsive choice rule. So you look at all the contracts, you rank them according to the preference relation that you have, and you choose them one by one from the most preferred one, and you go down the list until you fill the capacity or until there are no more contracts available to choose from. Okay? So this is the so-called responsive choice rule, and it will indeed satisfy path independence. Now, we're going to look at a choice rule that is used in the context of affirmative action or diversity. Now, we're going to introduce student types. For example, a type could be minority veteran. Right? So I'm a minority and I'm a veteran, and that's my type. So the types can depend on different characteristics, such as gender, race, ethnicity, and so on. And the set of all types is tau. And the school is going to reserve a number of seats for each type T, and the number is going to be called by RTC. The school wants to have at least RTC number of type T students. So they reserve that many seats. What is the choice rule? So first we start with the reserved seats. For each type T, we admit students with the highest rank according to the preference relation up to RCT. At the second step, we look at all the empty seats and we fill the empty seats according to the preference relation. So this is the so-called choice rule with reserves, and it also satisfies path independence. Any questions so far?
We see that this case rule is satisfied path independence.
I'm not going to show it, but it's not so. This one especially is not trivial. Yeah, so it needs approval. Now, so let's assume that there are many schools, and each school is endowed with a path-independent choice rule. we're going to claim that there exists a stable matching. But how do we find a stable matching? It turns out that the Gale-Shapley deferred acceptance algorithm can be used to find a stable matching. How does it work in our setting? Now, each student is going to propose to the school with their most preferred acceptable contract, right? So I identify my most preferred contract, and I propose to the school associated with that contract, right? If such a contract exists, if such a contract does not exist, the student doesn't propose to anybody. Each school C is going to consider all the contracts proposed to it, and it is going to tentatively accept the ones in the chosen set, and they are going to permanently reject the ones that are not chosen. At any step, if a student is rejected at the previous step, they identify their next most preferred contract. If such a contract exists and it is acceptable to the student, then they are going to propose to the corresponding school with that contract. Now the schools are going to consider all of the admitted contracts from the previous step, and they are going to consider the set of contracts proposed at this step. They are going to apply their choice rules, and they are going to tentatively accept the chosen contracts and permanently reject the rest. Okay. So this is the Gale-Shapley deferred acceptance algorithm in a many-to-one matching setting with contracts. So since each contract, so we are going to stop when there are no more proposals, and since each contract can be rejected at most once, we are going to end at a finite number of steps, because we assume that the number of contracts is finite. Now we can state our first result. So this is the existence result in our setting. Suppose that each school has a path-independent choice rule, then the deferred acceptance algorithm produces a stable matching. Now, Kojima Sensei was asking for a proof, so we will prove this result, and this will be the only proof in this lecture, I think. So the reason I'm showing the proof here is that the standard proof that you may have seen, especially in many-to-one matchings with contracts in a more general setting, uses lattice theory, and in particular, Tarski's fixed-point theorem. So these previous proofs usually relied on substitutability, and there was an underlying assumption about consistency or IRC. Now I'm going to show you a direct proof without using any mathematical tools, and we're just going to rely on the properties of path-independent choice rules. And I want to highlight that actually path independence is the right notion, and once you study with study path-independent choice rules, the existence is almost straightforward. So let's see how the proof works. So as far as I know, this is an original proof that I wrote for a lecture maybe 3 years ago, 4 years ago. So we know that the deferred acceptance algorithm is going to end at a finite number of steps, right? Let's call the number of steps T, uppercase T, and let's call the matching produced by DA Y. Okay, so this is a set of contracts. This is the outcome, and this is the last step at DA. To check stability, we need to check individual rationality and no blocking pairs condition. Let's start with individual rationality. Well, how about individual rationality for students? Each student only proposes acceptable contracts. Therefore, no student is matched with an unacceptable contract. And that's it, right? So we don't need to do anything else. What about individual rationality for schools? Well, let's consider school C. What do we know? At the last step, the set of contracts considered by school C is this, XC of uppercase T. The school applies their choice rule and gets YC. right? Because at the last step, every school considers the set of contracts proposed to them at that step and all the contracts accepted from before. And this is the union, and they must get YC back. Now we're going to use path independence. So we know that YC is equal to choice from this set XTC. Now I'm going to split it into XTC and the empty set. And I'm going to use the definition of path independence. So by path independence, this is the choice from XCT union empty set. Well, the choice from this set of contracts is YC by definition. And then we take the union with empty set, so we get YC back. So we prove that YC is equal to choice of school C from YC. So therefore, individual rationality for schools is satisfied. Okay. So this is just an application of path independence. Now, perhaps the more difficult part of the proof is showing that there are no blocking pairs. So what do we need for a blocking pair? We need to have a student. The student wants to match with school C using a particular contract, X. But the school, when they consider this contract with the set of contracts that they already have, they don't want to accept X. Right? So this is our definition of stability. A student wants to match with school C using a contract X, but the school doesn't want that contract. So we start with a contract X between a student S and a school C, and we assume that this contract X is strictly more preferred for student S than the contract that they are getting in set Y. The student wants to be matched with school C. Now, so let's introduce some notation. So let's take the set of all contracts proposed to school C throughout the deferred acceptance algorithm. So we're taking the union of all these sets that we've identified at DA, right? So this is the set of all contracts proposed to school C. What do we know? So the outcome for student S in DA is YS. And X is more preferred by student S. That means the student must have proposed this contract at a given step, right? Because the student starts from their most preferred contract, they go down their list one by one. They ended up with YS, but X is more preferred. So that means they must have proposed to school C with this contract X. So we can say that X is in this set XC. X was already proposed to school C. Now, what else do we know? If you look at the choice of the school from the set of all proposed contracts, we're going to get the YC back by path independence. Why is this? Well, the school at every step gets a new set of contracts proposed to them. They apply their choice rule. At the next step, they get more contracts. They consider whatever they accepted from the previous step and the new set of contracts that is proposed. They apply their choice rule again. And we just continue in this fashion. But path independence says that it doesn't matter how you chop up this set and apply choice rule. At the end of the day, you're going to get the same chosen set. You're going to get the choice from XC. Right, so that's where path independence kicks in. The set of proposals is XC, and it doesn't matter how we chop up the set and at which step students propose these contracts. At the end of the day, the outcome is going to be the same, regardless of the order in which the contracts are proposed. So the choice from XC is going to be equal to YC. Now, let's take this equation. So YC is equal to the choice from XC. Now I'm going to split XC into XC and X, because the union of set XC with the contract X is going to give us XC back. Now, and then we can apply the choice rule again. So by path independence, this term and this term are exactly the same. Now the choice from XC is equal to YC. We're taking YC union X. So we have the choice from YC union X. So YC is equal to choice of C from YC union X. So this is the set of contract that school C has at the end. This is the new contract that the student wants to add, right? The student wants to switch, and the student wants to switch with this contract. Since X is not in YC, X is not in this set. So X does not belong to YC because of this condition, because the student didn't have this contract, and the student actually strictly preferred contract X to whatever they had in matching Y. So therefore, X doesn't belong to YC, which means X doesn't belong to the choice of YC union X. So therefore, there are no blocking pairs. So I hope this is clear. So we're just using like properties of path independent choice rules, and that delivers us the existence of stable matchings in many-to-one matching with contracts.
Okay. So in the setting without the drug, we know that under the assumption of this consistency as a presumption, I think there's a maximal domain result that serviceability is sort of necessary condition. Then your proof makes me wonder whether, let's say, when we do not assume the ILC or consistency as a presumption, do you know whether path independence also be shown sort of this fundamental?
That's a very good question. Thank you, Kojima Sensei. So we have results showing that if you assume that the choice rules are derived from preferences, for example, like maximizing a utility function, or you assume the irrelevance of rejected contract condition, then substitutability is, in a sense, necessary to get the existence of a stable matching. We have a similar result for path independence. So I think Chambers and Yenmez 2015, I think the AJ Micro paper, I think has a result like that. So it is true for path independence. So let's say that there is a school and the school's choice rule does not satisfy the path independence condition. Then you can construct choice rules for other schools and preferences for students such that a stable matching does not exist. Furthermore, these preferences that you construct are really simple. For the schools, you construct preferences over individual contracts, and they accept at most one contract, right? So they have unit demand, and the preferences of the students are also really simple. So they just rank contract associated with them, and yet a stable matching does not exist. And yet, there are papers that show that under weaker conditions than substitutability, a stable matching still exists. So I think there are like Hatfield and Kojima JET paper, and there are some recent papers on this, that there are conditions weaker than substitutability in the many-to-one matching that will still give you the existence of stable matches.
In those kind of papers, I guess a key is that there are multiple that are given students to sign. And I guess this not one possible conjecture that if we are in the sort of more standard KHF setting where there's only one contact, so then maybe there's a chance that maximal result so.
Thank you. That's a really good point. So if in these papers, usually like a student and a school can sign more than one contract, and that's crucial in the violation of substitutability. And then it turns out that all these conditions actually are equal to substitutability if a student and school can sign at most one contract. Well, can a student and a school uniquely define a contract? So there is only one contract between a student and a school. Thank you. Now, the deferred acceptance algorithm is not only interesting theoretically. It turns out that in many matching markets now, we apply the deferred acceptance algorithm. For example, we use the deferred acceptance algorithm to assign students to public schools. And it has been used in many countries such as Chile, France, Sweden, and the United States. Likewise, the deferred acceptance algorithm has also been used to assign students to universities. And countries that have adopted the deferred acceptance algorithm include Brazil, Chile, Hungary, and India. And there are others. So in this context, one of the questions that we want to ask is whether a student should submit their preference relationship truthfully, or they should submit a different preference ranking in order to get to a more preferred school, right? So in other words, is the deferred acceptance algorithm strategy-proof for students? So we are only asking this question for students. Now, because we are in the, let's say that we are in this context and we are assigning students to public schools. In this context, public schools are not strategic agents. Their admissions criteria are commonly known. They are imposed by the school district and they are enforced. So they cannot strategically choose between students. Okay? Their choice rules are commonly known. Therefore, we are interested in whether students are going to submit their preferences truthfully to a centralized clearinghouse. All the students submit their preferences to the clearinghouse. We apply the deferred acceptance algorithm, and the matching is announced. So in such a setting, is it optimal for the students to submit their true preference rankings? So that's the question that we want to study next. It turns out that the deferred acceptance algorithm can be manipulated, so a student can get into a more preferred school by submitting a different preference ranking than their true preference ranking. This example is from Hatfield and Milgram. Let's suppose that there are 3 students, 1, 2, 3. There are 2 schools, A and B, and each student school pair uniquely define a contract. Okay, so there are no terms. The terms are fixed. The preferences of the students are as follows. Student 1 prefers A to B, and students 2 and 3 prefer school B to school A. And what about the schools? For school A, their choice rule is given as follows. If all students apply, then we choose the third student. If the first 2 students apply, we choose both of them. And if the third student applies together with either the first or the second student, we just choose the third student. If only one student applies, that student is chosen. If the third student is available, we just choose the third student and nobody else. If the second and the first students apply together, we choose both of them. The choice rule of school B is really simple. It is a responsive choice rule with capacity 1 and preference ranking 1, 2, 3. Now, let's see how the deferred acceptance algorithm works in this setting. The 3 students, A and B. Let's see if I will be able to do this without any mistakes on the board. Each student proposes to their most preferred school. Student 1 proposes to A, students 2 and 3 propose to B. So A accepts the first student according to this outcome. Now, B has a responsive choice with capacity 1, and the second student is more preferred than the third student. So the third student is rejected. That's the end of the first step. Now, the third student proposes to the next most preferred school, which is A. Now, if the first and third students apply together, school A accepts only student 3, right? If student 3 is available, then the school accepts only student 3. So the first student is rejected. The first student applies to school B. Now school B considers 1 and 2 together. 1 is more preferred than 2, and the capacity is 1. So the second student is rejected. The second student proposes to the next most preferred school. That's school A. School A considers 2 and 3 together because 3 is available, 3 is chosen, and 2 is rejected. And that's the outcome because there are no more schools that the rejected student can propose to. There are no more available contracts. So the outcome is, I want to use the notation that I have on the slide. So the first student is assigned to school B. The third student is assigned to school A. The second student doesn't have a matching, so the outcome is the outside option for the second student. Now we want to look at the second student, and we want to see how the deferred acceptance algorithm works if they report that A is more preferred than B. Remember, the second student's true preference ranking is that B is better than A. Now the second student is going to submit this preference ranking, which is not true. Okay. So S2 reports B, okay, A is better than B. Now let's see how the deferred acceptance algorithm works. So 1 proposes to A, 2 reports to A, 3 reports to B. Right? So let's go back and check the preferences. Okay, so 1 proposes to A. Now 2 is reporting this preference. So 2 also proposes to A. And then 3 proposes to B. Now A applies the choice rule to the set including the first and the second students. And the school chooses both of them, right? That was the choice rule. When 1 and 2 apply together, they are both admitted. The third, so B has a responsive choice rule, and the third student is acceptable. So B also accepts the third student. There are no rejections. So the deferred acceptance algorithm ends at the first step. And what is the outcome? So S1 gets matched with A, S2 gets matched with A, and S3 gets matched with B. Now let's compare the outcome for the second student. Here, the second student was matched with the outside option, so they were unassigned. And now they get matched with school A, and school A is acceptable. So therefore, the second student gains by manipulating and submitting a preference ranking different than their true preference ranking. In other words, the deferred acceptance algorithm is manipulable by students. Of course, we ask the same question. Well, the deferred acceptance algorithm in general is not strategy proof for students. So what do? We close shop and go home? No, right? As researchers, we say, okay, we want to push the boundary as much as possible. We ask 2 questions. So either we can simplify the notion of strategy proofness. Maybe we can come up with a weaker notion of strategy proofness and study whether this weaker notion is satisfied in general, or we come up with some conditions under which the deferred acceptance algorithm becomes strategy proof for students. In this lecture, we're going to take the second approach, which is the standard approach in market design. And we're going to ask, when is DA strategy proof for students? Now, the condition that we need is again going to be imposed on the choice rules of school. And this condition is called the law of aggregate demand by Hatfield and Milgram. Let me give you the formal definition first, and then we're going to talk about an interpretation. A choice rule C is going to satisfy the law of aggregate demand if for every pairs of contracts, a set of contracts, X prime and X, If X prime is a superset of X, then the number of contracts chosen from X prime is weakly greater than the number of contracts chosen from X. If you make the set larger and larger, you could not choose less. You could choose the same number of contracts that is allowed, but you cannot choose less when the set becomes larger and larger in the set inclusion sense. So why is this called the law of aggregate demand? Now, I'm assuming that some of you are students studying economics, and you've taken intermediate micro, or maybe a graduate level micro, right? So there's a law in economics called the law of demand. What is the law of demand? So the law of demand study is what happens when the price of a good goes up. When the price of a good goes up, the demand for that good goes. Okay, so this good becomes more expensive, the price goes up, so the demand for it goes down, right? So this is the law of demand. Now here, we're not looking at a particular good, we're looking at all goods. And when is it the case that we have less contracts to choose from? So that's the case when all goods become more expensive. Everything is becoming more expensive, we can only choose less, we cannot choose more. So then, the aggregate demand should go down. Okay? So this is the law of demand analogy, and that's why I guess Heckel and Milgram called it the law of aggregate demand. So we're looking at the demand of all the goods in the economy, and price going up means there are less contracts to choose from. And in that case, the overall demand should weakly decrease. So this property also has been named other terms. We can also call it size monotonicity. Now let's go back to our example when the deferred acceptance algorithm was not strategy proof for students and the second student could manipulate LAD. I'm going to claim that this choice rule does not satisfy the law of aggregate demand. So why is that the case? Well, if you look at the number of students chosen, when everybody applies, that's 1. When only students 1 and 2 apply, the number of chosen students is 2. There are less students to choose from, and the school is choosing strictly more. That's a violation of LAD. So LAD fails. Which choice rules satisfy the law of aggregate demand? So the 2 examples that we've seen, responsive choice rules satisfy the law of aggregate demand, as well as path independence. And the choice rules with reserves satisfy the law of aggregate demand, as well as path independence. Now, let's look at our second result. Suppose that school choice rules satisfy path independence and the law of aggregate demand. Then the deferred acceptance algorithm is strategy proof, meaning that it's strategy proof for students. Okay? So that means no student can submit a preference ranking different than their true preference ranking in order to get into a more preferred school. The best that I can do is to submit my true preference ranking. I don't need to strategize. So this is a safe strategy. And in the context of school choice, when we are assigning students to public schools, it is viewed as a condition that levels the playing field. Meaning that it doesn't matter, it doesn't matter what kind of resources you have. You don't need to know, much. All you need to know is your true preference ranking over schools. And by submitting that, you will get into the most preferred school that you can get into by submitting any other preference ranking. So you don't need to know the popularity of schools. You don't need to know the preferences submitted by other agents. It doesn't matter whether I go talk to my neighbors and learn what preferences they are going to submit. I can always do the best for me just by submitting my true preference ranking. So that's good. Now, the deferred acceptance algorithm has two different versions, right? There are two sides of the market. One side of the market makes the proposals. The other side of the market decides whether they are going to accept or reject. Now, one question that becomes important is whether the deferred acceptance algorithm is more favorable to the agents who are making the proposals, or it's more favorable for agents who are deciding whether to accept or reject offers. So let's study that question. We need the following definition first. A stable matching is student optimal if every student equally prefers its outcome to any stable matching outcome. So this means if a student optimal stable matching exists, then every student agrees that they are getting the most preferred school among all schools that they can be assigned to in stable matchings. From the definition alone, it is not clear whether a student optimal stable matching exists, because all students need to agree that they are getting the most preferred school among all schools that they can get into in stable matchings. However, from the definition, if a student optimal stable matching exists, it is unique, because we're assuming that student preferences are strict. If there's a student optimal stable matching, each student gets only one school that is the most preferred acceptable school among schools that they can get into in stable matchings. So therefore, the outcome is uniquely defined. So the matching is uniquely defined. So when do we get student optimal stable matchings? So our third result states the following. Suppose that school choice rules satisfy path independence. Then the deferred acceptance algorithm that we defined, in which students are making the proposals, produces the student optimal stable matching. For this result to be true, we are only imposing that path independence property is satisfied. We're not assuming the law of aggregate demand. So as long as path independence is satisfied, the outcome of the student proposing the deferred acceptance algorithm is going to give us the student optimal stable matching. So this result is not only interesting in theory, but also in a practical context. Right? We talked about different matching markers in which we are using the deferred acceptance algorithm. By choosing either version of the deferred acceptance algorithm, we are choosing for which side the matching is going to be optimal. So it has practical relevance as well. And this was especially important in the context of assigning doctors, residents to hospitals. In the United States, there is a centralized match that assigns doctors, residents to hospitals. And since 1952, the deferred acceptance algorithm has been used. Remember that the Gale and Shapley paper was written in 1962. So in practice, this algorithm was used before it was studied by academicians. Okay? And there, the question is, should we use the resident proposing one, so it's optimal for the doctors? Or should we use the hospital proposing one, so it's optimal for the hospitals? So in 1952, the algorithm that was implemented was the hospital proposing version. And in early 1990s, the residents match switched their algorithm to the resident proposing deferred acceptance algorithm. So I think it's not on the slides, but I should note that a student optimal stable matching is also school decimal. So we haven't defined what school passimility is, especially because there are choice rules, but there's a way to define it. A student optimal stable matching is also school passimal. So when you're favoring one side, you're actually making the other side the worst among stable matchings. Okay? So this is a really important question in practice, which version of the deferred acceptance algorithm to implement. So another important question in the context of assigning doctors to hospitals is whether we can increase the number of doctors in a region, say in rural areas. Right, so in the United States, it turns out that there are not enough doctors in rural areas. So therefore, one question was, if we believe in stability, right, and we want to implement stable matchings, we don't need to use the resident proposing or the hospital proposing deferred acceptance algorithm. There are many matching mechanisms in which we get stable matchings. Can we increase the number of doctors in rural areas by implementing a different mechanism? The answer turns out to be no, because of the following results. Suppose that school choice rules satisfy path independence and the local aggregate demand, then each agent has the same number of contracts in every stable matching. So that is, if a hospital can admit 5 doctors, but they're assigned 3 doctors in a stable matching, they will be assigned 3 doctors in every stable matching. It doesn't matter whether you use the deferred acceptance algorithm or another mechanism. As long as the matching implemented is stable, you do not increase the number of doctors. And furthermore, a stronger version of the rural hospitals theorem is true, in fact, that you get the same set of doctors in all stable matchings if the hospital cannot fill its capacity. So this is a very relevant question, I guess, in the context of Japan, and Kojima Sensei can tell us more. But there was a question of whether we can increase the number of doctors in some prefectures, right? So perhaps, the demands for hospitals in the Tokyo prefecture is a lot, because a lot of people want to live in Tokyo. But the demand for hospitals in other prefectures is low, and I think there was a policy of the government to increase or to get a more fair distribution of doctors among prefectures. So, but this result tells us that if we don't change the mechanism, we're not going to change the distribution of doctors in prefectures. So therefore, we need to change the mechanism, and different mechanisms have been proposed. Kojima Sensei, so I know that you've studied these mechanisms, and I wonder what mechanism is used right now in Japan.
Right now, basically the algorithm with the modification that the hospital capacities are actually sort of so that the total number of positions is upper bounded by government.
So still, I guess, so one way to control the distribution of doctors is modifying the capacities at different hospitals. For example, you can reduce the capacities of hospitals in the Tokyo prefecture so that the number of doctors assigned to hospitals in Tokyo is less. Therefore, more doctors are assigned to other prefectures. And I think, so if I understood Kojima Sensei correctly, so this is the mechanism that is used right now in Japan. Now, let me conclude. So I want you to remember a couple of things before we move on to the second lecture tomorrow. One, stability is a desirable solution concept in two-sided markets. Our first result says that the deferred acceptance algorithm produces a stable matching if school choice rules satisfy path independence. Our second result says that the deferred acceptance algorithm is strategy proof if school choice rules satisfy path independence and the law of aggregate demand. So the key takeaway from this lecture is that path independence and the law of aggregate demand are crucial properties in market design. So if you're proposing a particular choice rule to be used in a two-sided matching market, then it would be good practice to check if the choice rule that you're proposing satisfies path independence and the law of aggregate demand. If these two properties are satisfied, you don't need to say more. You can just say that by the known results in market design, we can study a two-sided matching market in which schools use the choice rules that I proposed. And we will get all these nice results. And just a reminder that today's lecture was on basic theory of stable matchings. We're going to have 2 more lectures. Tomorrow's lecture is going to be Matroids and greedy rules and in matching. And our last lecture will be on market design with deferred acceptance. So that's the end of today's lecture. Again, thank you all for coming.
Wonderful. So, very good, very good. Okay, so any questions or comments?
I want to know about the example which is the choice rule satisfies the path independence and low aggregate demand, but the choice rule doesn't match to the responsible word.
Oh, I see. So yes, there will be choice rules satisfying that property. So a choice rule that satisfies path independence and LAD, but not responsive. Let's see if I'll be able to get the right example in this try. Students and 2 schools. So I think, okay, so this one satisfies LAD and path independence, but it's not a responsive choice rule, right? So why is LAD satisfied? So you need to check that. You need to check when you go down along these arrows or nodes. You don't choose more, right? So 2, 1, 2, 2, 1, 1, 1, 0. So LAD is satisfied, and you can check that path independence is also satisfied. But now it's not a responsive choice rule because even though, like, if it is responsive, it looks like the capacity should be at 2, and the preference ranking is like S1 and S2 are better than S3, and S1 is better than S2, and all the students are acceptable. But here we're just choosing 1 student instead of 2. If it was a responsive choice rule, then we should have chosen both students. Well, I'm glad that I got the first rule in the first try. Oh, it satisfies substitutability. Oh, I see. Maybe I didn't get it at the first try. No. I mean, the easiest way to see it, we may need more examples. So if you look at choice rule with reserves, right? Like you may need like 4 students and just 1 reserve type, but choice rule with reserves is more general than responsive choice rules. So you can construct an example in which you have reserves, but the choice rule is not responsive. So basically, sometimes you need to favor some students, and as a result, it cannot be generated by using the same preference ranking over students. So that will be a short answer, and then we can look at it over lunch. We can construct one over lunch. So that's correct. Yes. Any other questions?
I have a question. So in today's lecture, or in the literature of matching with contract in general, school's preference is usually represented by choice rule. But alternatively, we can think about the kind of the objective function or preference order or something to represent school's preference or something. I don't mean responsive the preference over the set of contract,
sure,
or something. So so why do you think this choice set specification is more popular and believed as attractable or something?
So I think there are 2 reasons. So one reason is that if there's an underlying utility function over sets of contracts, then of course we can look at the choice rule. Right? However, I think the choice rule approach is better in at least 2 ways. So one of them is that in practice, if you look at schools, in all applications, like schools don't have utility functions, but schools give a procedure to admit students based on some criteria, right? So if you look at, how school districts admit students, it's schools have the capacity, they may prioritize some students, they may reserve some number of seats for schools and so on and so forth. So in practice, institutions usually do not have utility functions, but they have a procedure like a choice rule to admit, say, students or workers. So, and the second one is like, if you look at the definition of stability, the utility function per se doesn't matter. As long as we have the constructed choice rule, we can check whether the matching outcome is stable or not. So we don't really need the cardinal values that the school assigns to packages of students, but what we need is the induced choice rule in order to check whether a stable matching exists or not. And likewise, if you look at an outcome that's implemented in practice, and if your theory is that the outcome is stable, then you can have some ordinal implications of that. So you can have some implications on the choice rule, but you can't have any cardinal implications just by looking at the matching outcome.
Thanks. Yeah, so to me, I initially, thought that, basically, in many important applications, the schools have kind of, some objectives, and the choice rule is, kind of, defined or characterized by such a kind of, objective function or something. But in reality, there are kind of many situations where schools have some choice rule, but do not have any clear objective functions to.
But one of the fundamental questions in economic theory that you can ask is whether a given choice rule can be rationalized by an underlying utility function.
Yeah.
And we have some recent work on that.
Yeah. Thank you so much.
Thank you.
As an empirical question, I'm wondering about how to check the from after we test. And first question is that it's possible to check the condition from the after we test. And the second question is that if the condition looks like violated, it's like we violated to some extent, how should we proceed to empirical
That's a good question. So if I understand your questions correctly, the first one is in practice, like if you have some data, can we check whether the path independence condition is satisfied or not? For example, in particular, if the data is aggregate, so meaning that maybe like students are put into different categories, and then you have some information about the matching on the categories or the choice on categories. So I think if you have individual data, right, on all sets of contracts, then obviously you can check path independence. But that is requiring too much. So like you need to have the data set on all possible sets of contracts. However, if you put more structure on it, like let's assume that the data is aggregate and the school doesn't actually care about the identities, the school only cares about the characteristics that the student has. So then, in that case, I think it will be easier to check whether path independence condition is satisfied or violated. But I mean, we don't, as far as I know, so we don't have a good theory of that. And the second question is like, if there are violations of path independence or the law of aggregate demand, so what do we do? So it turns out that like in the setting with matching with contracts, so the choice from all sets of contracts is not important because we never see a student proposing with, a student having two contracts. Or like think about the deferred acceptance algorithm, a student doesn't use two contracts to propose. Therefore, the important choice of the schools is all sets in which each student has at most one contract. So therefore, the properties of the choice on these sets is important. And there's a recent paper published in Restat, so they show that stable matchings exist under observable substitutability. And so if observable substitutability is satisfied, even if path independence is violated, then a stable matching is still going to exist. But the question is, let's say that observable substitutability is violated, what do we do? Then the answer is not clear to me, but I can answer the following question. If, let's say, path independence is satisfied, but the law of aggregate demand is violated, what do we do? So in that case, you can actually expand the choices of the school. So the school chooses more contracts, but you still respect the capacity of the school, and both path independence and the law of aggregate demand are satisfied. So there's a way to do it. So as long as path independence is satisfied, if you violate LAD, you will be able to add more sets, more contracts to the chosen sets without increasing the capacity of the school. And you'll be able to satisfy both path independence and the law of aggregate demand. So, and the reference is, so for this one, Chambers and Yenmez, AJ Micro, 2015? Yes. Any other questions? Yes. Yes.
Sometimes school priorities. In that case, is there this definition of the notion of the study? I think this notion was very important. Generalization.
So the question is like, what do we do when school priorities are weak and there can be ties? So as long as there is a well-defined choice rule, our definition and our results will hold. But then what happens? Let's say that the priorities are so coarse that we cannot actually define a good choice rule, right? So I think Kenzo-san has a paper looking at choice rules with ties. But in the context of two-sided matching, there has been some work studying that. But it's a hard problem. So, like usually, so I think in two countries, Chile and Hungary, the priorities are weak, and policymakers want to either accept all students with the same score to the school, or they want to reject all students with the same score. So they want to have a clear cutoff score so that all students above the cutoff either go in, are accepted, or the ones below the cutoff point are rejected. But in this context, I think we don't have clean results such as the ones that we have. In particular, I think, for example, strategy proofness is violated for the proposed mechanisms.
So the discussion is assumed that the set of available contracts is finite. So can some results be generalized to continuous?
So there is some recent work on settings with, say, a continuum of contracts. Actually, even if you go back to 1970s, for example, Shepley and Shubik have studied one-to-one matching markets with continuous transfers. So you can view this as the setting in which there's a continuum of contracts, and it's each contract is identified by a monetary payment. So there are papers studying these settings, and there is also now a recent literature in which there's the continuum of agents on either one side of the market or both sides of the market, and people have also studied these markets.
More questions or comments? Okay, yes, one more comment or question. So I really loved your resistance cell, I mean the proof using the plastic furnace. So I wonder whether you also have some like some new proof using basically just using plastic furnace or other results that you say. Are they more similar to just like just
That's an interesting question. So I haven't tried it with the other results. So and then the reason that I came up with this proof was for another lecture that I prepared a while ago, and I wanted to see if path independence can be applied without relying on Tarski's fixed point theorem. I think it should be possible to come up with simpler proofs, but I don't know how simple they will be.
Okay, I see. Okay, so on that note, so let's finish the first lecture. And again, so we have two more lectures, one on Tuesday and another on Friday. So everyone is welcome to that. And okay, so let's thank both. Thank you very much.